Welcome everyone. Thank you for joining us for today's webinar. My name is Arnold and I'm the Marine Business Manager at Veritas Marine Singapore. Just an administrative announcement before we get started. If you have any questions during the presentations, please do not hesitate to raise your questions through the Q&A function, and we'll endeavor to go through them at the end of all the presentations. Today, we are pleased to share with you a webinar on the topic of the current state of the art of hydrogen fuel cell, presented by our panel of speakers. Well, intrinsically carbon-free fuels such as ammonia and hydrogen are under development to become the basis for zero carbon shipping. Fitting vessels to store and use hydrogen represents a significant cost, lower energy density related to the fuel, and new challenges for its safe use. As such, BV is supporting the marine industry with rules on fuel cells and sessions like this to increase our understanding of the technology. We are glad to have four excellent presenters with us to address the topic of hydrogen fuel cell. We have Mr. Bruno Delanois and Mr. Guillaume Daniel from Bureau Veritas. We are also very pleased to have Dr. Frank Verbeck and Mr. Thomas Grosjean from Helion Hydrogen Power. Before we start the presentations, let's take a poll to see your views on the topic of hydrogen as a fuel cell. Sorry, hydrogen as a fuel. So the first question is, do you think hydrogen fuel cell can be a competitive solution to fulfill MARPOL greenhouse gas reductions in the coming decade? Let's give us half a minute to take in the answers, and we'll go through the poll results. Okay, we still have the polls coming in. Okay. With that, let's have a look at the results. We can see that actually 82% of the audience here feels that yes, hydrogen fuel cell is a competitive solution and is one of the more promising fuels for sustainable shipping. Well, whether or not your thoughts on this topic have changed by the end of the session, we certainly hope you'll find it informative and aid your decision-making processes with regards to hydrogen as a future fuel for sustainable shipping. Our first speaker, Bruno, is head of the electricity and automation section within the design assessment department of the assessment department. Bruno holds a degree in electrical engineering from HEI and a DEA in electrical engineering from Lille 1 University in France, and a DESS in administration from IEA in France. With that, I would like to hand over the floor now to Bruno. Bruno, you have the floor, please.
Thank you, Arnold. In the first part of this presentation of this webinar, I would like to make a technical background on fuel cell. So in the next slide, I'm going to remind you some basics, and I'm going to present you the different technologies available and their characteristics. So the content of my presentation will be the following: first, hydrogen, then fuel cell basics principle, and then fuel cell technology. So first, hydrogen. Why starting with hydrogen? Because hydrogen is the most commonly used type of fuel in fuel cell technology. This is not the only one. We may have methane, we have ammoniac, we have methanol, but hydrogen is the most commonly used. And in addition, this hydrogen is most of the fuel cell admit hydrogen as fuel. Be careful, don't make the confusion between the gas you have in your tank and the gas you have in the fuel cell. You may have hydrogen in the tank, hydrogen in the fuel cell, so easy. But you may also have methane in tank and hydrogen used for the fuel cell. It means in the middle, you have a kind of reforming system to transform hydrogen to transform methane in hydrogen. Hydrogen is not so well known in the marine. We use for a long time methane, so methane is very well known. Hydrogen, not so much. Forward, I would like to explain you, to remind you the characteristic of hydrogen. It's very important from a safety aspect, because when we integrate the fuel cell on board, we'll have to manage the safety, and we need to know what are the hydrogen characteristics. So hydrogen is a dangerous gas. There is a large explosivity range from 4% to 75% compared to methane 5 and 15. There is a very low inflammability energy, 17 microjoules, so very small. So it is a very dangerous gas. ATEX characteristic is 2CT1. But advantage is that this gas is very light. It means it will dissipate, dilute very quickly in air. So this is a big advantage. There is a very low boiling point, minus 253 degrees. It means it's very difficult and energy consuming to have liquid hydrogen, very high density, and a very high flame temperature, nearly invisible. We have on this picture 2 slides, one from a normal camera, one from an infrared camera. So with a normal camera, we don't see the flame. It's invisible. With the infrared camera, we can see the flame. So the flame is nearly invisible. Hydrogen is present on Earth in very large quantity. You have hydrogen in the water, in the methane, but this is an atom of hydrogen. This is not a gas. This is not the gas. It means we need to produce the gas. There are some very rare cases where the hydrogen is stored in underground deposits, but it's very rare. So we need to produce hydrogen. Hydrogen has a color. It's not the gas itself, but the way we produce it. Depending on the source and the process, on the find a color to hydrogen. The hydrogen naturally present on Earth in underground deposits, this is white hydrogen. But most of the hydrogen we use at the moment, this is gray hydrogen. It means hydrogen produced from methane or coal with a process called reforming or gasification. So this is not clean hydrogen, this is gray hydrogen. On the opposite side, we have what we call green hydrogen. This is hydrogen based on renewable energy and produced through electrolysis. So in this case, this is a very clean hydrogen. So in the middle, we have blue hydrogen, turquoise hydrogen. So this is hydrogen based on fossil energy, methane, coal. But with blue hydrogen or with turquoise hydrogen, we make sure we'll capture the CO2, either the gas or at the gas level or at the solid level. With turquoise hydrogen, we try to catch the CO2, the carbon with solid. So once we have produced hydrogen, we need to store hydrogen before we use it on board. So there are different means to store hydrogen. It may be either physically based or material based. So physically based means the hydrogen will be compressed. So in container, in tank. So there are different levels. It may be at 350 degrees, 500 degrees, 700 degrees, so 700 bars, sorry. So very high level, very high pressure. Storing hydrogen at a liquid phase, it's not so easy because remember the boiling point of hydrogen minus 253 degrees. So it's very energy consuming. Other possibility is to use a material-based approach. It means we have containers with porous material and the hydrogen is stored within the material. For the moment, what we see the most is compressed gas, so at a pressure between 350 bars, 500 bars, 700 bars. Now let's have a look at the fuel cell basic principle. So first, fuel cell is not something new. It exists for a long time. The invention of fuel cell is disputed, depending if you speak of prototype fuel cell or more laboratory curiosity. But it is commonly admitted that fuel cells were invented by an English guy, an English lawyer, William Grove, in 1873. He created a fuel cell based on sulfuric acid and platinum electrode. And then fuel cell was developed step by step, and different type of fuel cell were developed. On the last century, the NASA, the American Space Agency, made also a lot of improvement in the fuel cell technology. So a fuel cell, how does it work? You have on the left side an anode, on the right side a cathode. So the fuel is injected at the anode side. So the fuel may be liquid or gas. At the anode will happen what we call an oxidation. At the cathode side, we will inject air. What we want in the air is oxygen. On the cathode side will happen a reduction. In the middle, there is an electrolyte. This electrolyte is permeable to ion, but not permeable to electron. It means the electron will follow another way and will be used to generate a current. The ion may go either from the anode to the cathode or from the cathode to the anode. It depends on the technology we use, and this is what we will see afterwards. So very important slide. What are the different types of technology? In fuel cells, this is a generic name. There are plenty of technologies. There is what we call alkaline fuel cell, direct methanol fuel cell, proton exchange membrane fuel cell, solid oxide fuel cell, molten carbonate fuel cell, phosphor acid fuel cell. All these fuel cells have different principles. The first, the fuel is not the same. As I said before, most of them can work with hydrogen, but not all of them. For instance, the direct methanol fuel cell can only work with methanol. The electrolyte is not the same. Electrolyte may be either liquid or solid. This electrolyte may be acid or basic. The operating temperature is not the same. Most of the fuel cell can work, I would say, at normal temperature, but some particular fuel cells, such as the SOFC, have to work at a very high temperature, 800 degrees, 1000 degrees. Lifetime is not the same. On starting time, a very important parameter, may be very different. SOFC, for instance, need a long time before it can start. So BV has start to have a good experience now in fuel cell, and we work a lot on PEMC and SOFC. PEMC, so proton exchange membrane fuel cell. Helion, our partner today, is a well-known manufacturer of PEMC. SOFC, we have a good experience with Bloom Energy, for instance, this type of fuel cell. Now let's detail a little bit more the different fuel cell technologies. So this is exactly the same slide as before, but with specific detail for this PEMC. So on the anode side, we inject hydrogen. On the cathode side, we inject air. The hydrogen will be oxidized. It means a proton will go from the anode to the cathode, and the electron will go through the electric circuit. I remember you that a hydrogen atom is based on a proton and electron. It is a very simple atom. It means when this atom has lost its electron, it becomes only a proton. So when we say H+, H+ is a proton. That's why we call this type of fuel cell PEMC, proton exchange membrane fuel cell. This kind of fuel cell, the theoretical voltage is around 1.23 volt. This is very theoretical. In reality, we have much less. We have around 0.7, 0.8 volt per fuel cell. If we go a little bit more into the detail for this fuel cell, this PEMC fuel cell, what do we have? At the anode side, on both sides, I would say, we have a bipolar plate. What is a bipolar plate? It is a plate with tubes on the gas, so hydrogen on one side, oxygen on the other side. This gas will be injected. Then we have different layers. We have a gas diffusion layer. This is a porous material, and the gas will go through this material. After we have a catalytic layer. It is catalytic layer will facilitate exchange and will facilitate the reaction. So all these layers form what we call the MEA, the membrane electron assembly. It may be obvious, but I say it in a bipolar plate has two sides. So if we have, for instance, on one side of this bipolar plate, we have tubes for oxygen, but there will be another side for this bipolar plate where we will inject hydrogen, but hydrogen of the following fuel cell. So we have bipolar plate with two sides. At an assembly level, how does it work? So we have a bipolar plate. We have in the middle the MEA, membrane electron assembly, which is based on this porous material, catalytic material, and so on, electrolyte. We assemble everything together. We assemble different cells in order to create a stack, and this stack will create energy on board. So we need to assure the proper pressure to make sure all the contacts are properly done. Second technology I would like to mention today, the two important technology. We have discussed PEMC. Now let's discuss SOFC, so solid oxide fuel cell. Same principle are nearly the same. We inject hydrogen on the anode side. We inject oxygen at the cathode side. This fuel cell work, the electrolyte will be different. We work at a very high temperature. And in this case, the ion going, the ion in the electrolyte is not H+, it's not a proton, it is oxygen ion. And the oxygen ion will go from the cathode to the anode. In the former case, oxygen, water was created at this level, at the cathode side. In the SOFC fuel cell, water is created at the anode side. So there is some slight difference between all this type of technology. A fuel cell cannot work alone. A fuel cell needs plenty of auxiliaries. So the fuel cell stack is installed in a kind of cabinet. This fuel cell will need, for sure, hydrogen. So on the right side, you have hydrogen coming from the gas from the tank. You have the master gas valve. You have the block on blick valve. Then you need to reduce the pressure to inject hydrogen at quite a low pressure, just a few bars. And there is this recirculating pump for the hydrogen. We need air. Air will be supplied through high-speed compressor. It will be injected in the fuel cell. There will be, you need to cool this fuel cell. That's why we have a cooler at two levels. We have a high water cooler for the fuel cell. We have a low cooling system for the compressor. We have humidifier in order to facilitate the exchanges at the fuel cell rack. This fuel cell, I told you, is installed in a cabinet. It will be a gas-tight type cabinet with hydrogen detection. This cabinet will be highly ventilated. And the key point here will be the status of this cabinet. Do we consider this cabinet as hazardous or not? And the experience we have with different clients is usually they manage to demonstrate that because when we compare the potential leak of gas, leakage of gas, and the airflow, there is a very low probability of explosion. This is what we call hazardous area of negligible extent. So we managed to install standard electrical equipment in this cabinet. So in conclusion, I would like to say that fuel cell is a whole principle, but with very interesting perspective. There are plenty of development nowadays in order to improve the reliability, the maintenance, the safety, the energy available. There are some challenges. Safety challenge is important, but also the regulatory frames challenge as rules are still under development. And I think this is a good transition for the next presentation. Back to you, Arnold.
Thank you, Bruno. Now that we have heard about the technology, let us explore more into the rule. Our second speaker, Guillaume, is one of BV's rule development engineers. He holds an engineering degree from the École Centrale de Nantes and specializes in power engineering. He is actively involved in the development of rules and notes related to fuel cells and hydrogen, and closely follows the international and IMO developments related to gas-fueled ships, hydrogen, and fuel cells. With that, I would like to hand over the floor now to you, Guillaume. Guillaume, you have the floor, please.
Sorry, forgot the mic. Yes, let's have a discussion on the H2 and fuel cell regulation. I intend to show you what's already existing, what is not yet covered in that field. And then in the second part, I will go into more details on what is inside the PV rules dedicated to fuel cell. Just small issue. Yes, marine industry is considered as a dangerous industry. That's why, in consequence, there are many regulations and safety that were developed. The most famous is the SOLAS Convention. Most of you will know that. But this convention was developed having conventional fuel in mind. It does not cover low flashpoint fuel. It means fuel with a flashpoint below 60 degrees. So in the last years, there was a need to develop specific guidance for those type of fuel, especially natural gas. And in 2015 was published the IGF code that cover the gas fuel chip with general requirements applicable to all kind of low flashpoint fuel and detailed requirements on natural gas. Concerning fuel cell and hydrogen, hydrogen is pretty obvious that it falls under the IGF code scope. So the general requirements are applicable. Concerning fuel cell is a technology. It's not a fuel, obviously, but the its safety concept is really influenced by the fuel it uses, and the fuel used by fuel cell are mainly low flashpoint fuel, as presented by Bruno. It was a fuel cell discussion at the IMO level was included in the IGF code scope. Those guidelines are now finalized. They were finalized at the end of 2021. They should be approved at the next Marine Safety Committee at the end of the month. So we can hope to have guidelines very soon. Concerning hydrogen, the work has only been initiated at the end of the year, so it's really beginning. So we will have to wait a little bit more to have a complete set of requirements at the IMO level. Concerning the BV rules, BV guidelines already existed for a long time. The first version was issued in 2009, but it needed to be updated to be aligned with the IGF principles. That was published later. So a new version of this rule were published at the beginning of 2022 in January. So I will go into more details later on this. We are also working on a new rules for hydrogen. It's under preparation. It will cover the bunkering, storage, and supply aspects of hydrogen with a dedicated notation that is hydrogen fuel, and for ship planning to be converted later to hydrogen, hydrogen fuel prepared notation. That is also under preparation. So just a few words to conclude on that part. Note that even if there is no dedicated regulation existing, the use of innovative technology is still possible. In general, you have rules that will cover parts of the technology of the system, either from at the IMO level or at the PV classification society level. And there is always a SOLAS alternative as a design approach that is a really powerful tool and that can be used for innovation. Two other idea, it's when you have a new project with new technology, the involvement of flag administration is really important because you will have to validate such project. And risk assessment is at the core of the process. So this is something you will have to do. You will have to take special care because it's very fundamental. So that was a brief overview on that topic. Now going into more details on the NR547, that is the new our new rules for ship using fuel cell. First thing to have in mind is that this rule was not meant to work alone. Those rules are dedicated to the fuel cell system. So this is what you can see on the right side of this picture. It covers the fuel cell system, the fuel reforming, if you have any, depending of the technology and primary fuel you want to use. But you have to use it to cover the whole system. You have to use it with other rule notes dedicated to the primary fuel. So if you have the list on the left side of the potential fuels that can be used, that we have thought of, and you will have to use other rules to cover storage supply. For hydrogen, you have generic rules in NR 529 that are applicable while waiting for the future rules. Another important idea concerning the scope of this rule note is that it's applicable to all the existing fuel cell technology. Bruno mentioned that there are two favorite, I would say, two technologies that are more mature for the marine industry, that are PM and SOFC fuel cells, but it's possible to use other technologies. So these rules were meant to be applicable to every kind of technology and configuration. Below you can see a picture with the balance of plants, the different elements that are covered by these rule notes. You will of course recognize the fuel cell module at the center. So the rule note includes specific requirements for those elements. For the fuel cell modules, it will be pretty detailed. For more common elements, for example, the power conditioning system, it will refer to already existing rules, for example, NR5467 for steel ship or other rules. So it's all inside the NR547, but it will refer to the other one. Now I will just give you some information in a concept that is really important to understand when you open this rule note. It's a fuel cell space concept, because most of the requirements will apply to this space. So what is it? Fuel cell space. It's a space. It can be a room, an enclosure, a casing, which will contain the fuel cell power system. It means where you can find the fuel. So, for example, where you can find this hydrogen if you are using hydrogen. And the fuel cell space, it's casing, the room that will be able to contain the gas. And all this, most of the requirements, most of the strategy, the safety strategy, will apply to this space. So it's very important to define it very well at the very beginning. And you have two possible strategy. You can either ventilate that space, kind of prescription, and this, or inert it with also specific rules on this. So this concept is pretty important. As I said, there is prescriptive requirements in these rules, but we still rely heavily on the safety assessments. It's at the core of the process, because you have to consider that there are many different technology, as Bruno presented you. There are many possible configuration on different uses. So safety assessment is really necessary. There are different possibility of risk analysis depending of those configuration. For example, if it's used for essential services or not. You have to take into account if there is a need for explosion analysis, for example, for ventilated fuel cell space. And possible toxicity consequences. It can be optional. It depends if, for example, if you are intending to use ammonia or methanol. So it depends of the fuel, or if you are using a technology of fuel cells that can produce carbon monoxide, can be toxic at some level. So you have to take all that aspects into account. I will go quickly through the other domains that are covered. So many different aspects. For example, the material compatibility, because at some point in general, you have hydrogen inside the fuel cell. So with hydrogen, we have embrittlement risk that can lead to leakage. There's always an issue. You have elements of the design of the fuel cell, fire safety, detection, extinguishing system, the definition of the hazardous area, and a lot of requirement, I would say, on the monitoring system to check if there is a process deviation and safety action to secure the fuel cell. So I won't go any further into the details. If you have any question, please ask. We'll try to answer it. And I would let Arnold speak. Back to you, Arnold.
Thank you, Guillaume. Right, before we dive into the next segment, let's take some time to see your views on the existing hydrogen fuel cell product. So we have for poll question 2, which of the following is hydrogen fuel cell capable to provide energy for? Basically to do with the sizing. What do you think is your requirement, or what do you think is available now? And we shall hope to have more information on this in the coming segment. This is just to see your views right now. Okay, the polls are still coming in. Okay, they've stabilized now. And with that, we can see that actually most of the audience feel that, you know, the current application, or maybe their ideal application for hydrogen fuel cell would be for the lower power, and then with a middle group, you know, from middle power from 1 megawatt to 8 megawatts. And then we have a small group that feel that maybe they should have something, I believe, for 8 megawatt, which I don't believe is in the market right now. And we also have a third poll question. Okay, the poll question is, how do you imagine the use of fuel cells on board? Do you think that it will likely be for the main propulsion, for auxiliary power, or for harbor power supply? Or you may be undecided and hope to wait and see and learn more about it. Let's take some time for your polls. Okay, polls are stabilized now. Okay, we have 38% who believe that, you know, the fuel cell technology should be for the main propulsion, while the majority, which is 44%, believe that it is for auxiliary power, with a smaller minority, you know, thinking that it should be for harbor power supply, and also 9% who are undecided. You know, so far we have looked at hydrogen fuel cell from a technology and class perspective. We shall hope to hear from our experts from the equipment maker perspective next. Our next speakers are Dr. Frank Verbeek and Mr. Thomas Grosjean from Helion Hydrogen Power. Frank is head of R&D and engineering within Helion Hydrogen Power, a company of the ALSTOM group. He holds a PhD in hydrogen safety and joined Helion as safety and reliability product manager and hydrogen safety expert in 2010. Since then, Frank has worked as project developer and technical coordinator at European institutions and is the head of business development. Frank and his team work actively in the development of heavy-duty fuel cells for rail, maritime, inland shipping, and genset applications. His colleague Thomas is Marine Project Engineering Manager at Helion Hydrogen Power. He holds a master's degree in Maritime Project Management and joined Helion as Project Engineer Manager for Marine and Inland Applications. During his time in engineering school, Thomas created an association gathering more than 20 students and professors to develop a small hydrogen boat. This catamaran was propelled using a hybrid system composed of a 5 megawatt hydrogen fuel cell and batteries. This demonstrator won the Energy Boat Challenge 2019 in Monaco as the first hydrogen prototype. With that, I would like to hand over the floor to Frank. Frank, you have the floor, please.
Good afternoon and good morning, everybody. So today with Thomas, we're going to talk about the current state of the art of hydrogen fuel cell. So first of all, we both work for Helion Hydrogen Power, which is an old startup having more than 20 years experience in high power fuel cell. Within Helion, we develop, manufacture our own stacks, the core technology, which is a proton exchange membrane technology using graphite fuel cell plates to ensure the highest durability and typically more than 20,000 hours. Within Helion, we also develop a fuel cell system from 100 to 2 megawatt systems. And we target regional trains, obviously. We target locomotive trains. We're working currently on mining, construction, and material handling, maritime and inland barges, and power generation and backup. For more than 1 year now, Helion has joined ALSTOM group in order to develop our industrial facility and increase our full services coverage. Typically, we've been invested in automated stack productions, allowing to produce more than 30 megawatt per year fuel cell systems. We have a test facility gathering more than 14 test bench, climatic test chamber, and allowing to re-inject more than 1 megawatt on the grid. Here on this slide, you can see a few references of Helion. On the left-hand side, it's not very known, but Helion was one of the first developer of a hydrogen locomotive together with the French operator SNCF. We've been also joined ALSTOM, which is a pioneer in hydrogen trains, with more than 60 trains sold in Germany, France, and Italy. Then we can see on the middle picture on the top part that we have developed the largest green hydrogen platform in France, in operation for more than 10 years, and gathering different technologies: photovoltaic farm, electrolyzer, fuel cell hybridized with a battery, and refueling station. We've been working actively on green data centers, and we've provided also backup solution for a nuclear crisis war room for the French Atomic Energy Commission. And on the bottom part, you can see that we are working actively on marine and inland applications. On the bottom right, we are currently working on a 2 megawatt project for shore-to-ship system, and is going to be detailed a bit later on with Thomas. We are also working on a hybrid hydrogen dredge, the first contract that we won very recently. So why Helion? Helion has many differentiators. We have more than 20 years experience, a significant track record in complex solution with while maintaining these complex systems. We are clearly focused on heavy-duty applications, on stationary, rail, and maritime projects, and we can provide you tailor-made solutions in order to improve your total cost of ownership. And of course, we have been working at different areas of the globe and provided engineering studies for European, but also Asian and American clients. Today, Helion is a part of ALSTOM group and benefit many synergies from these new interactions. ALSTOM has a full worldwide coverage with more than 230 sites, and we can provide added value for integration, maintenance, and different services around the world. ALSTOM is a robust group and has a clear vision of hydrogen strategy, and is currently investing a lot on such a technology. And we are going to provide also ALSTOM Health Hub services to improve the maintenance of our systems.
Thank you, Frank, for this introduction. Now I would like to present our new product line dedicated to the marine application, which is called Navy Fuel Cell Power Unit. So this product is composed at least of fuel cell stacks that allows to have electrical power up to 207 kilowatts. We also have various power configuration depending on the customer request. Our design is based on a cabinet. That means all the components are accessible from one side. That facilitates the customer to the maintenance. The main technical data are written on sorry, I missed something. We also include into this product a hydrogen enclosure with dedicated ventilation system and continuous hydrogen detection. That means that the room do not have any hazardous area outside the boundaries. Now the main technical data are written on the screen. You can see the voltage range of the fuel cell power unit is from 500 volts up to 850 volts in DC power. The vessel should supply a cooling loop, a continuous cooling loop with a maximum temperature of 37 degrees. And because we are developing a heavy-duty system, the fuel cell power unit can run up to 25,000 hours without any stack replacement. Also, in order to supply hydrogen, we need a minimum of 10 bar of hydrogen for the fuel cell power unit. Our objective, our target is to have a type approval certificate during the next year. Now let's continue a bit deeper on the process of the fuel cell power unit. As you can see, the main component of the fuel cell power unit is the hydrogen enclosure, where you can find all the components with hydrogen. We also have the fuel cell stacks combined with their own balance of plant and their own control units. All that part form what we call fuel cell module. All around that, we have also the process air management in order to feed the stacks of air and the cooling system, the internal cooling system. All these auxiliaries are controlled by the fuel cell power control unit. On the left side, you can see all the inlets of the fuel cell power unit. You have the ventilation inlets, the hydrogen inlet from the storage, and also the air inlet for the process. Also, you have the communication between the fuel cell power unit and the ship control system or the power management system, depending on the application. All our systems are fully autonomous. That means each fuel cell power unit can be controlled independently. On the right side, you can see all the outlets. So the first is the ventilation outlet. Then you have the process exhaust. On the bottom part, you have the water exhaust and also the secondary cooling loop supplied by the vessel. On the right side, you also have the power made by the fuel cell stacks that goes through first DC-DC converter that can be controlled by the fuel cell power control unit, and that can this power converter can feed a DC bus with batteries, for example, and we can implement also another stage of conversion that can feed a ship power grid. Now let's see our first application. The Jagger and the project Hydromare was signed the 1st of April, so last week. So this Jagger will be armed by the region Occitanie and will be built by the shipyard Piriou in France. Also, this vessel will be certified by BV. It is an hybrid system, an hybrid vessel, sorry, with a diesel generator and hydrogen system. It is propelled by 2 azimuth propeller. So the Helion solution is a complete fuel cell system that's able to supply 200 kilowatt net. This system is connected to a 690 volt AC bus, and all the system is integrated into a container on deck. This product is also combined with batteries, so it's an hybrid system, fuel cells batteries, that allow the ship to are fully autonomous, only with the stack running, without any diesel generator running for the hotel load. Now, back to you, Frank.
So on this slide, you can see what could be the extrapolation of a 1 megawatt containerized turnkey system, fuel cell system. On the right-hand part of the container, you can see a first compartment that we could call the fuel cell compartment, which is enveloped by a A60 fire insulation. You can see that on both sides of the container, you have rows of fuel cell power units separated by a non-hazardous area corridor. Each fuel cell unit, each fuel cell power unit is linked on the left-hand side to a DC-DC converter, each fuel cell power unit representing a branch. Each of these DC-DC converters are connected to a battery bus, which is also linked to a DC-AC inverter to re-inject AC power on a client bus on 50 or 60 hertz solution. Such a complete system is equipped with a proactive and a predictive maintenance system that we call the ALSTOM Health Hub, and is going to be deployed on several projects. Here you can see a simplified electrical architecture that I described before. So you can see in the middle, each fuel cell power unit, FCPU, is linked to a DC-DC converter. You have 5 branches of DC-DC converter connected to a battery bus, which is linked to a DC-AC converter that provides AC current to the vessel grid. Each fuel cell power unit has its own command electronic, and all the command electronic of each FCPU is linked to the master command box that communicates communicates with a vessel automation system, but also our ALSTOM Health Hub device. So as a conclusion, we could say that now Helion is a part of a worldwide group leader, ALSTOM, which is a pioneer in hydrogen trains. Helion benefits for more than 20 years experience with an important track record in large complex solutions in operation and maintained by Helion. We clearly focus within Helion on rail, stationary marine applications, and on that last field, we are developing our 200 kilowatt fuel cell power unit, especially for marine applications. We can provide tailor-made megawatt scale solutions with hybridized system integrated in a container or engine room. And as Thomas mentioned, we target a type approval certificate in 2023 with Bureau Veritas. And we announced the first contract that we won with our 200 kilowatt fuel cell power unit for the project on a dredger in the frame of Hydromer project in France. Thank you. Back to you, Arnold.
Thank you, Frank. With that, we shall go ahead and take some time for questions now. Just a reminder, please be sure to type your questions into the Q&A. But I don't think we have any shortage of questions. There are so many coming in. I apologize, I have to be quite selective. So we have one that has been asked 3 times. I believe this will be for Guillaume. In relation to the BV rules in progress, can you give some estimate as to when it will be published, specifically for the hydrogen fuel rules?
Yeah, of course. I was hoping for this question. Yes, you have to understand that the rules are developed alongside with project. So it's a ship needs time to be built, and so the rules needs time to gather experience and to be able to have something that is credible. So I would say for the timeline, it's not. We are working on projects, so it's not next month, but it won't be in 2 or 3 years. It will be something in between.
Okay, thank you, Guillaume. I think we also have one question for Frank and Thomas. There's a lot of interest about regarding your first project. So the question is, what is the overall efficiency of the 200 kilowatt fuel cell system that will be installed on board? And maybe coupled with a second question, can you explain or elaborate on is there any leftover hydrogen in the process exhaust? And precisely what is the process exhaust for this project?
Okay, so for the first project, the project Hydromer, we have the fuel cell power system, fuel cell power unit, with an efficiency around 55%, depending on the efficiency of the power conversion system. For the process exhaust, we have a common exhaust for air and hydrogen. So we only have a few particles of hydrogen that are continuously leaking into this process exhaust. We are reducing at the minimum the quantity of hydrogen on this exhaust in order to first, if we can, do not have hazardous area and ATEX area, and the other one in order to improve and increase our efficiency. So now we are around 5% of hydrogen leaking regarding the consumption of all the system.
Okay, thank you, Thomas. Maybe we go on to the next question. I believe maybe Bruno can shed some light on this. In comparison with the different fuel cell technologies, there's a question that goes, can methanol be used as the fuel for hydrogen fuel cell or for any other fuel cell for that matter?
Well, you know, at BV we don't promote any particular technology, and we support all of them, and we try to provide smart requirement for all these different technologies. So methanol, this is feasible for sure, but for the moment we don't really have experience with methanol. The two most technology we see, they are PEMC and SOFC. So we have a good experience with different manufacturers. So both are quite efficient technology, and not suitable for all application. You know, SOFC, you need some time to start your fuel cell. So you cannot select. You have to select the technology depending on your application. But the two technology we see the most is SOFC and PMC, and in particular PEMC. This is the most commonly we have now. It starts to be a very proven technology now.
Okay, so is methanol currently being used for PMFC?
No, PMC. In PMC, it is proton exchange membrane fuel cell. So it means proton, necessarily you need to use hydrogen inside the fuel cell.
Okay. But methanol can be used in a SOFC setting.
Or in a direct methanol fuel cell. There is one technology specific to methanol, but the methanol for the moment is not so common. So it is PMC, SOFC, I would say.
Okay. Thank you, Bruno. Okay, we have one question directed to Daniel. Guillaume, do we need cofferdam for the fuel cell room? And how is the hazardous zone in relation to the fuel cell room, perhaps adjacent to the fuel cell room? How is it considered?
I would say the use of a cofferdam will really depend on the configurations of the ship. So we'll need a general arrangement, something more precise to answer to this question. Considering the dangerous area, the basic the idea in the rule note is that the fuel cell space, I come back to this concept, is considered as a zone 1 dangerous area. But depending of the fuel cell, it's possible using the right standard to reconsider and within the risk analysis to consider that it's only a zone 2 if it's in the big, if it's a small fuel cell in a big room, for example, it can happen to reduce classification of the area.
Okay.
So it's really configuration dependent.
I see. So in that sense, there's another question related to this and use of maybe A60 insulation. You know, how effective is our traditional fire insulation? You know, considering that hydrogen fire temperature may be different, you know, from what is currently being combusted on board. You know? Is it going to be very much different? You know, in terms of like having A60 boundaries, or is it you know, going to be similar? You know, what do you think, Guillaume?
I think for the fuel cell, we stick with what we know, with which means A60 insulation and so on. You have to keep in mind that in the fuel cell space, you don't have so much hydrogen, in fact, in general, and the main idea for fire safety is to shut off the supply.
Yeah.
So hydrogen won't last long if it burns. For the storage, it will be another issue.
I see. Okay, then I think specific to the new project we have, I think there is a lot of question about that, you know, for Frank and Thomas. So how does the hydrogen fuel cell impact the overall cargo hold volume? You know, maybe with specific you know, parallels we can draw from the question from your current project. You know, what is the reduction in maybe dead weight that we're looking at for this project that we have now?
Yeah, I think okay. The first project, so Hydromer, all the hydrogen storage and all the fuel cell system is installed on deck, so it doesn't affect the cargo space.
Okay.
That means that all the components are on deck, so you don't have specific room inside the vessel for our technology for this project.
I see. So
and we have for the storage there is 4 container of pressurized hydrogen, so that allows the vessel to work 1 week without any storage replacement without any bunkering.
I see. Okay. But I think it's also stemming from what we know from the hydrogen fuel is that it has low energy density. So it moves on to the next question is, for ocean-going vessels, vessels that are going to trade over longer distances, with hydrogen storage and low volume energy density, are there any, solutions at Helion to develop or potentially solve these issues for larger vessels, ocean-going vessels? What do you think?
Okay, for large autonomy, indeed, the large autonomy and large power, there is clearly currently, let's say, an issue because, as it was said, storage of gaseous hydrogen takes a lot of space, and if we talk about high power and high autonomy, the whole complete system, fuel cell and storage would take too much space in the engine room or on the deck. That's why for the coming years, and probably we're going to move with different fuels, not gaseous hydrogen, but probably liquefied hydrogen. We can talk, it was mentioned by Bruno, ammonia, ethanol also. So that's currently type of technologies that we are currently looking at for storage in order to fuel and convert these fuels into hydrogen that will be used in our high power fuel cell systems. And typically we can talk about a few megawatts. But we can see that, okay, the technologies, they're emerging, but it will require a bit of time to move completely to such a new systems for storing hydrogen.
Okay, thank you. So next question, I believe for Bruno, and maybe Guillaume, step in if needed. What is the specific consideration for fuel cell firefighting? Does an aerosol generator type system, is it compatible with hydrogen fuel cell firefighting, or is there a specific firefighting medium that we need to use?
But as Guillaume said, at the fuel cell level, it will be quite easy to manage because the idea or the plan is to switch off hydrogen supply as soon as we detect something. So I would say at the fuel cell level, it will be managed quite easily. At the storage level, it's a little bit different, and I don't know so well this part. I've seen in the Q&A some point concerning hazardous area. This is something very important. As we have seen in the Frank on Guillaume presentation, there are plenty of auxiliaries all around fuel cell. But it may be very difficult if we consider this zone as hazardous to have all these fans, compressor, everything of a safety type. So usually, what I have said before, if there are some, we manage to consider the fuel cell as non-hazardous. It's not a statement; it is a demonstration we need to have. But if we compare the possible leakage on the ventilation flow, which is very high in this part, we manage to demonstrate that we will be far below the LEL, and in fact, the risk of explosion are very limited. This is a hazardous area of a negligible extent. So this is very important because it gives the possibility to manufacturers to install standard equipment, so to limit the complication and to limit the cost. But this is a demonstration. This is fully admitted and defined by IC for hazardous area. And then, so it and as soon as we detect hydrogen, we switch off. And in the worst case, we should be far below the LEL. So this is the philosophy to limit risk of explosion at the fuel cell level.
I think that's a very interesting train of thought. We will have two questions related to that. Bruno, if you may, I will come back to you on that. But before that, let's go for an intermediate question with Frank. So typically, our audience would like to know how large is this fuel cell? How large, maybe for the 200 kilowatt one that we have now? And then later on, leading on to the next question, which what Bruno has mentioned, can they be eventually in the future installed in a normal machinery space, without special ventilation? So Frank and Thomas first.
Yeah, so depending of what we are talking about, if we are just talking about the fuel cell power unit itself, so the assembly of stacks and all the auxiliary, so the main dimension is a 2 meter to a 2.1 meter length, 0.7 meter width, and 2.2 meter high. So this is a fuel cell power unit that produces DC power. Now, if you add a power conversion system, all the electrical components and equipment, and depending also on the application, if we need to install batteries, if we need to install DC-AC inverter, the space of the room might be subject to modification. And so if we are just talking on the fuel cell itself, I'll give you the dimension, but if we install inverter, it depends on the power.
In any case, we can tailor our solutions depending on the size available and the electrical architecture of the complete system. We can adapt our technology and our architectures to the client's one.
Okay, thank you. So we come back to Bruno and the consideration of installing such equipment in a normal machinery space. Guillaume, please feel free to also chime in if you can add. Yeah, Bruno.
Not easy question because I cannot anticipate too much. I know each ship, each installation is subject to a specific risk analysis where we'll try to anticipate and to the possible risk of leakage. First important point, there is this possibility of hazardous area of a negligible extent, which help a lot for the installation. Keep in mind also, a fuel cell is not only the fuel cell. You have all this double wall pipe, the block and bill valve. You have all this piping system coming from the storage. So you need to consider the full. You need to have the big picture and to consider the risk coming from all the different parts of the installation. But our experience is that we managed to facilitate a little bit the installation of fuel cell with a nearly normal room with high ventilation flow, with direct exhaust outside the room. So it's during the last application, with installation was as we managed to simplify a little bit the installation. But this is really a case-by-case study. So it's all installation we have seen were different, slightly different. So we need this is a case-by-case study.
Okay, understand.
Just to complete the answer, to complete the answer from Bruno, at this stage, the rule not exclude the installation of a fuel cell system in a machinery space that is used for other conventional diesel engine, for example. So it will be necessary to prove that there is no additional risk to install it inside. So the demonstration has to be done if we are to go beyond this requirement.
Okay, so we follow on to the next question. Hydrogen. How due to risk of hydrogen gas leakage. What is the ppm or LEL that we're looking at? Is it a prescriptive one or strictly based on risk analysis? Guillaume, is there a ppm level?
In general, we are based on the low explosivity limit, which is 4% of hydrogen in volume.
Okay.
Which is based for all the works we have.
So explosivity is between 4.5 and 75, so it is a very wide limit. Yes. And usually we have an alarm at 20% and safety at 40% of this LEL.
Okay. I think with that, we will have to close because we're running out of time. Before we come to an end, let's have some time to have a closing remark from each of our presenters. Bruno, your closing remark, please.
So very exciting period nowadays. A lot of investment, development perspective. We have experienced manufacturers with proven product. According to me, the key point now will be marinization. Manufacturers need to be a bit flexible and to adapt to the maritime requirements and maritime good practice. But I'm quite positive. We have
exciting times. Thank you, Bruno. Guillaume, closing remark, please.
Yes, as I said, rules are developed alongside with new projects, and so please go ahead, propose new project, and we'll go with you.
Thank you, Guillaume. Frank?
Yeah, so as a concluding remark, I would say that Helion with ALSTOM demonstrate that hydrogen can run on trains. And now we are at an exciting period for maritime and inland barges, and we are here to support potential clients and projects.
Thank you, Frank. Thomas, your closing remark, please.
Yes, so yeah, I'll just complete the sentence of Frank. In fact, yeah, we show that the market is pushing to have a solution. So that's why we are working with BV in order to launch our product as soon as possible and to obtain the certification, the right certification, and go quickly and demonstrate that the technology can work on vessels.
Thank you, Thomas. So our sincere apologies, we are not able to answer all the questions due to time constraints, but we welcome you to email us your questions so we can follow up with you accordingly. We've come to the end of our webinar. It was our pleasure having you with us today, and we look forward to seeing you in our next webinar. Thank you.